Hi everyone, we are going to be going over 12.2 today. So here's a list of all data of iPhone sales during their opening weeks. You have the different iPhones, the years, and how many millions of units sold. Use a calculator to create a scatter plot of the data with the year as an explanatory variable and units sold as a response. Sketch the scatter plot above. So I'm going to draw out. We have years on the bottom and units sold in millions. And I'm going to show you on the calculator how I'm going to do this. Alright, so you plug in, you go to Stat Edit. I'm going to clear this. And for L1, I'm going to plug in 2007. I don't know why it didn't clear it. Okay, here we go. 2007. Nope. 2007. 2008. So do this along with me. Make sure you can do it. And then for L2, we're going to have the units sold in millions. Okay. And now we're going to create a scatter plot. So second plot, I want it on. It's on scatter plot mode and list 1 versus list 2. So then I can do zoom stat. Okay, here we go. It wasn't working, but now it is. So this is our scatter plot. And I'm going to put it on the page. Okay, so looking at our calculator, the scatter plot looks a little bit like this. Would you use a linear regression model to model the data? Sketch the residual plot below and support your explanation. So we're going to plot a residual plot. To find the residuals, we're going to go to StatCalc and run a linear regression between list 1 and list 2. And I get my values. Now I'm going to add my residuals to my lists. And we're going to press second, stat, and 7 for resid. All right. And then I'm going to do a scatter plot of L1 versus L3. All right, so when I'm looking at this residual plot, I clearly have a pattern, and it looks like a curved pattern. And since we have a leftover pattern, it's not a good not a good model. So I'm going to go back to the screen. So we said that when we have our residual plot that has a leftover pattern, it is not a good model. So here's our leftover. We have like a curved pattern. And we're going to say that the linear regression is not a good model because there is a leftover pattern in our residual plot. All right. Next, since we expect it's nonlinear, so we looked at our data, it wasn't linear. When we checked the linear model, it said it wasn't good, which is no surprise because this does not look linear, it looks exponential. So what type of model do you think it is? We're going to say exponential. And then the general form of an exponential function is a times b to the x power. And then it's asking, what is the inverse of exponential? The inverse function of an exponential function is a logarithmic function, or a logarithm. And so here we go. This is like kind of the beginning of the new stuff. How do we transform our data? How do we transform an exponential function? We are going to log both sides. The logarithm is the inverse of the exponential, and so it undoes the exponential function. So we're going to log both sides. And log is the opposite of the exponential. So we're trying to get our data in linear form. So we're logging both sides to get rid of the exponential equation. Okay. Now we have logarithms, but we're going to use some logarithm properties right now. When we're taking the log of two things and we're multiplying them, we actually get to say, to expand it, we do log of a plus log of b to the x. So this is like a logarithm property. You learned it in pre-calc and in algebra 2. In pre-calc, you learned why this is true, but right now we don't really care why it's true. We just need to remember that when you're multiplying two values inside of a log, you can expand it. And then another property is that the exponent here can come to the front. So I'm going to rewrite this with log y equals log a plus x log b. Okay. Now you will notice, you might notice, that we actually are in like a linear form at this point. So this is looking similar to y equals a plus bx, where this is our b value, or our slope. We have the x because b is multiplied by the x. This is our a value, or our y-intercept. And then our input is still x. But now, instead of our output being y, our output is log of y. So if you need to go back and kind of watch that, you can. But this is how we transform our data. We're transforming it to be linearized. The reason why we don't have linear data, this is exponential data, but all of our tools that we have available, like R squared and R and S and all these things, they're only available if we have linear data. So we're taking our exponential data and we are linearizing it to make it look like a linear equation. All right, let's go to the next page. Okay, so now we're going to, remember we had our x and our y, but now we're concerned with x as our input and log y as our output. So to get these values in your calculator, I'm actually going to make L5 be the log of L2. So I'm going to, if this was list 1 and list 2, I'm going to log all of my L2 values and put this in list 5. Okay, so I said that I was going to, I'm going to skip L4. I'm going to make L5 be all my log y values. So I'm going to go to the top And I'm going to say I want to log all my L2s. There we go. Now, these are the log values of the y values. So I'm going to write that in on the page. And I'm going to now make a scatter plot of the data with years the explanatory variable, years since 2000. So instead of 2007 and 2008, I'm going to make it 7, 8, 9, 10. And then on the y-axis, we're going to have log of units sold. So let me go and do this with me. Change all of these to just 7, 8, 9, 10. Okay. And now we're going to scatter plot L1 versus L5. Zoom stat. So 7 to 2015, and we're going up to 1.5. And our scatter plot, it looks a lot more linear now. Okay, so I made a scatter plot, and now our data looks linear. Calculate the least squares regression lines. This would be S or LS or L. And write it below. So I'm going to do stat calc 8 for linreg, and I'm going to do L1 versus L5. And I get an equation of A equals negative 1.55 plus 0.18 x. But remember, we are predicting this. So I'm going to put the y hat, and then I'm going to write that this is log of y, log of units sold, hat is equal to negative 1.55 plus 0.18x. Oh, whoops, hold on. Not x, but years since 2000. Okay, do you think the regression line is a good fit? Why or why not? Use the residual plot and sketch below. So now I'm going to do a residual plot of my x values versus my log y values. So I'm going to make a residual. And on my calculator, I'm going to stat edit. I'm going now to list 6, and in list 6, I'm saying second stat, and then 7 for resid. Now I have new residuals, and now I'm going to scatter plot L1 versus L6. Now my scatter plot looks a lot better. There's no leftover pattern. And that means that our data is good. Okay. According to this model, how many iPhones should be sold in 2015? So we're going to use our equation, log of units sold is equal to this, and then I'm going to plug in 15 here, and remember this is hat, and then I should end up getting plugging this in my calculator. 15 times 0.18 minus 1.55 and I'm getting 1.15. But I still have this log of units. So to get rid of the log, I'm going to base 10 both sides. And so I get units sold is equal to 10 to the 1.15 power, which is 14.1 million phones sold. Or, you know what, I'm going to say about. And interpret the residual. So residual is A minus P, actual minus predicted. Our actual in 2015 was 13, and then our predicted is 14.1. So 13 minus 14.1 is negative 1.1. So that means that the actual amount of iPhones sold in 2015 is 1.1 million less than predicted. Okay. Now, we're on the next page. When we have an exponential model, remember we used to have x comma y, but when we use the exponential model, we look at x and log y. Okay, and you can look at the explanation on the other page or before. Now, if we have a power model, we're also going to log both sides, but it looks a little bit different. So I'm going to log y, and I'm going to log the other side. And then I get to break these up. Log a plus log x to the p. And then the p can go in front, so I get log y is equal to log a plus p log x. Now, this is still a. This is b now. P is now our slope. This is our y-intercept. And now our input is log x, and our output is log y. So this is going to be log x and log y. You can also use natural log. But remember, the base of natural log is e. So log base e of x is equal to natural log of x. So just remember that instead of like base 10ing, so to get rid of a log, we base 10 both sides, but if you have a natural log, we would base e both sides. Okay, I will say that this stuff is a little harder to comprehend, but the main things you need to remember is if your data is not linear, so if data is nonlinear, try logging the y values and see if that makes your scatter plot linear. And if that doesn't work, then try logging the x and logging the y values, and then that should be linear. Okay, let's do a problem together. We are given our regression analysis. The constant is our a value, our y-intercept. The number next to our variable is going to be our slope. So I'm going to write this. Our least squares regression line is hat number of balloons is equal to 45.008 plus 10.809 times height cubed. They gave us that they had to cube the x values. Suppose you want to fill a box with a height of 8 feet, so you just plug in 8 for height. Don't forget to cube it though. And then when you plug this into your calculator, 8 cubed times 10.809 plus 45.008 is about 5,579 balloons. So we predict that for a box with height of 8 feet, we would need about 5,579 balloons. Okay. Last problem, and then your homework is doing examples 3 and 4. Here we're given mortality rate versus income for different countries. This is clearly nonlinear. They used natural log. They natural logged both the x and the y's. And they gave us this information. So they gave us the constant, which is the y-intercept. They gave us the slope. They gave us the x and the y, the input, the output. So here we go. We're going to do our prediction. Natural log of income, they said, was equal to 11.495 minus 0.9374 times the natural log of under 5. It's like under 5 mortality rate. Why? Oh, you know what? I wrote this in the wrong answer. Give the least squares regression line. There's our least squares regression line. Part A asked, why did they use a power model? Well, they used a power model because they went from x comma y, and then they started using natural log of x and natural log of y. So that's how we know they used a power model. Okay, we have our least squares regression line. And then interpret the slope and the coefficient of determination in context. So our slope is negative 0.937. So we can say as the natural log of under 5 mortality rate increases by 1, the natural log of income decreases hold on, I need to say we predict our model predicts a 0.9374 decrease in natural log of income. Okay, coefficient of determination is r squared. They gave us the r squared value is 92.7. So that means that 92.7% of the variation in natural log of income can be explained by a linear relationship with natural log of mortality rate under 5. Okay. Using the model, predict the income per person for Turkey, which has a child mortality rate of 20.3. So this is kind of sad stuff we're working with. But we're going to predict the the income when our mortality rate of children under 5 is 20.3. So natural log of 20.3. Okay, and to get rid of the natural log, we're going to E both sides. Base E both sides, so we're left with income is equal to E to the power of all this, 11.495 minus 0.9374 times the natural log of 20.3. So in your calculators, you're going to do E to the power of 11.495 minus 0.9374 times the natural log of 20.3. And you should get about 5,902. So our model predicts that the income per person for Turkey with child mortality rate of 20.3 is about $5,902.